Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutewa Sos Ugobela Wemets. And without any further ado, let's look at these questions that we have here. Okay, so we have question 5, still on stoichiometry. It says sulfur dioxide has a pungent, irritating odor similar to the smell of a just struck match. Although its chief uses are in the preparation of sulfuric acid, sulfur trioxide, and sulfides. Sulfur dioxide is also used as a disinfectant, a refrigerant, a reducing agent, a bleach, and a food preservative, especially in dried fruits. The balanced equation for the decomposition of sulfurous acid, H2SO3, is as follows. Then 2 samples of H2SO3 with equal mass of which one is pure and one is impure are placed in open containers. Note that, are placed in open containers on a balancing scale as shown in the diagram below. Then they say, the graph below shows the results obtained and the graph becomes, note that, becomes parallel to the x-axis when the reaction is complete. So those two statements are very important. Now, obviously, looking at this here, you can see that this is an open system because there is no lid here or stopper closing here. And then this is obviously of the impure sample because some of the impurities are left down here. And then 5.1 says, explain why the mass of the flask with its content decreases. Now, obviously, because this is an open container, we know that it will allow the gases to escape, right? So with an open system, this is a system that allows the gases to escape the reaction sample, right? So that will be our reason, because the SO2 will be able to escape since this is an open system. It is open, right? So obviously, if the SO2 is able to evaporate, then over time, when you check the masses of the content in the flask, then you will then realize that it keeps on decreasing. So our reason for that should be this. The flask is open. The SO2 gas can escape, and thus the mass will decrease. Right, so I hope that makes sense. And then 5.2 says, at which time did the reaction of the pure H2SO3 stop? When did it stop? Now remember, they said the graphs become parallel to the x-axis when the reaction is complete. So that means we have to check where the graphs start to become parallel. But then here we are talking about at which time did the reaction of the pure. So we are looking at the pure. Down here, we are given the keys. So the one, there is a broken line is representing the impure solution, and then the solid line is representing the pure solution. Now that means we are looking at where the pure solution starts to be, the graph of the pure solution starts to be parallel to the x-axis. Where does it start being parallel to the x-axis? Now, obviously, when you check here, you can see that all the way down here, it's decreasing gradually so, and then somewhere around here we can see it starting to be parallel to the x-axis. So we can say let's count the number of blocks in here. That's 1, 2, 3, 4, 5, right? So this we can use it to find the interval between 6 and 7. That's only 1 unit, but then there are 5 blocks in between. So that means each block will be representing 0.2, right? So that means it's 6, 6.2, 6.4, 6.6, and then 6.8, then 7, right? So if we say it starts being parallel somewhere here, then we can tell that that's somewhere at 6.4, right? So it's just a prediction. It can be 6.4, maybe they can even accept 6.6, right? So between 6.4 and 6.6, when I look at your memo, it says 6.4, 6.6, it awards a mark there. So, okay, for 5.2, we're going to say the reaction stops at 6.4 seconds, right? Now, do not be fooled by this. The fact that the reaction goes all the way up until 10 seconds doesn't mean that the reaction stops at 10 seconds. Remember, the reaction stops the time the line becomes parallel to the x-axis. So that means the reaction was left up until 10 seconds, but then the reaction was actually complete at 6.4 seconds, right? So it was just left for recording purposes up until 10 seconds, but then actually the reaction came to completion at about 6.4 seconds. So it's just a matter of understanding that. So I hope it makes sense. And then let's now look at 5.3. So what is it that we have now? Now 5.3 says calculate the change in the mass of the pure sample H2SO3, right? Now to calculate the change in mass, obviously we need to see this clearly here. So calculate the mass of the pure. Again, note of the pure sample, right? So we are looking in the change in mass of the pure sample. So that means to calculate that, we'll just say change in mass is equals to the mass finally minus the mass initial, right? Now the mass finally will represent the mass of the pure sample when the reaction is complete. So here at 6.4. Now, what is the mass of that? So if we just trace this line all over to that point, so just trace the line to that point. So obviously you'll be having a question paper there with you. And then here, the interval is still the same. It's 1, 2, 3, 4, 5 blocks in between. But then the distance in between 110 to 120, that's 10, right? So we can say 10 divided by 5. And then we see that each block there will be representing about 2 units or 2 grams, right? So if that is so, that means in this case, we will have 110, 112, 114, and then 116, right? So the mass finally will be 116 grams, right? And then the mass initially, we can all see they start at a mass of 160 grams, right? So both the impure and the pure sample. Remember, they said they both have equal mass. Then that's 160. So if you say 116 minus 160, we get that the change in mass is negative 44, right? So negative 44 grams. So that means negative 44 grams of the pure sample has been used up during the reaction. So we had a total of 160 grams, but only 44 grams was used up during the reaction. So that's the meaning of that. So that's how you were just supposed to calculate that for 3 marks. Okay. And then let's now look at 5.4. Now 5.4 says calculate the percentage yield of the impure sample. So now I get that there was a confusion around this question here, because most of the time you are used to calculating the percentage yield of the pure sample. Now this time around you are being asked to calculate the percentage yield of the impure sample. Now to calculate the percentage yield of pure, we know that the formula is mass of pure over mass of impure multiplied by 100. But then now, because you are calculating the percentage yield of the impure sample, note that the equation now has to be mass of impure over the mass of the pure times 100. So this was the change that occurred here, right? So I get that when you are used to this, that question might be a bit confusing. So now note that the key here was that we are calculating the percentage yield of the impure sample and not the percentage yield of the pure sample. So what we needed to use is this here, right? So now let's start. So all we are supposed to do now is we're going to say, okay, we want the percentage yield of impure, right? And then therefore we're going to say the change in mass of the impure and then over the change in mass of the pure. Remember, we must use the reactant, right? So what is the change in mass of the impure? Remember, we haven't calculated it, but we can calculate because we know that the broken line represents the impure. Now, this again is mass finally minus mass initially. We already have the change in mass of the pure. From the previous question, we got negative 44. So there is no need to redo that one. So mass of the finally for the impure, we have to follow through here. And then we can see that the reaction comes to completion right at that point there. So if we can just draw that line to follow there, we can see that it's in between that block. Remember, we said each block here represents 2 grams. So that's 132, 134, and then up here it's 136. So if it's in between 134 and 136, then that means that's 137. Because as we can see, this line here is drawn in between here. So in between 134 gram and 136 gram. Now, if you can just check the average between that, you just simply have to say 134 plus 136 divided by 2. And then the average between those numbers will give you that mass, which is 135 grams. Now, that's our mass final, 135 grams. Right. Then our mass initially, obviously, is that 160 because they all started with 160 gram. Over negative 144. But let's not forget multiply by 100 because we are looking for the percentage. Then multiply by 100. Now we find that the difference in between here from the 160 all the way to the 135, it's negative 25. So negative 25 divided by negative 44 multiplied by 100. Then you simply just have to punch this into your calculator. And then you get your solution is 56.82%. Right. So this is the percentage purity of the impure sample. So note that the trick here was all on having to know this formula here. To know that this time around it will be the change in mass of the impure over the change in mass of the pure. And then everything that you had to do was just simply use the information provided. Okay, so let's proceed. Okay, so we are given a statement here. So we know that if we are given a statement just before the questions here, that means this statement here applies to the questions that follow underneath. So we have 100 gram of SO2 has now reacted with 50 gram of oxygen gas according to the following balanced equation. So we are given the balanced equation here. And then 5.5 says calculate the number of moles of SO2 and O2, right? So now we must calculate the number of moles of both this. So it's simple because we are already given 100 gram SO2 and then 50 gram O2. So let me open up a new page for that so that we are able to do this along with 5.6. Okay, so note, we are given 100 gram of SO2 and 50 gram of O2. Now to calculate the number of moles of SO2, it's just simply mass over the molar mass. Now the mass is 100. And then what is the molar mass of SO2? We know that sulfur, according to our periodic table, is 32. And then oxygen is 16. So that's 2 times 16. Now, when you do all of that, you will get 64, right? And then 100 divided by 64, that's 1.56 mole, right? And then again, let's do it for oxygen gas. We have mass over the molar mass. And then our mass was 50. But then the molar mass of oxygen gas, remember, these are 2 atoms of oxygen. Each is 16, so that is 16 multiplied by 2, which will give us 32. Then 50 divided by 32, again, it's 1.56 mole. So we can see that they both have the same number of moles, right? So that's all you needed to do for 5.5. But now, let's look at our question in 5.6. It's now saying determine which substance is the limiting reagent, right? Determine which substance is the limiting reagent. We know that the limiting reagent is the substance that will be used up first in a chemical reaction. Now remember, if we are to continue with this, we know that what we just calculated here, these are the available number of moles. So both of these are the available number of moles. So to continue and calculate the limiting reagent, all you have to do now is to calculate the required number of moles. Now remember, I always say use the second compound or molecule as the reference, right? So we want to use the O2 here as the reference. So that means my reference number is this one. Now what I mean by that is that I will say, what is the ratio of SO2 to the ratio of oxygen gas? Now when we go back to our balanced equation, we can tell that that's 2 is to 1, right? So that's simply 2 is to 1. Now, what is the available number of moles for the SO2? That's 1.56. Remember, I said this one is the reference, right? So for the one that is the reference, I just simply put X here. So I'm trying to calculate the required number of moles of the oxygen gas. Now, when I cross multiply here, this is 2x. Then when I cross multiply this is 1.56. Divide both sides by 2. Then my X value is going to be 0.78 mole, right? Now, this is the required number of moles. This is the required number of moles. Now, what does this mean? Obviously, we know that if the number of moles available is greater than the number of moles required, that means that particular substance is in excess. And then if the number of moles available is less than the number of moles required, then that means substance is limiting, right? Now using that, let's use our reference. Looking at this is the required number of moles, and this is the available number of moles. From here, we can tell that number one is satisfied because the number of moles available are actually greater than the number of moles required. So which makes our O2 here to be what? The excess reagent. Now, because we know that the nature of the chemical equation is that if one is in excess, then the other one has to be limiting. Since now we have concluded that oxygen gas is in excess, that means in conclusion we can say therefore SO2 is the limiting reagent, because remember, if one is the excess reagent, then the other has to be the limiting reagent. So in conclusion, we can then say SO2 is the limiting reagent, right? Because we have proven that oxygen gas is actually in excess, right? So make sure that you play this video as many times as possible and just try to understand the approach that I took in here. I know that some of your teachers at school might have different methods. So if you feel that you understand the method from your teacher, you can use that one as well. But then I feel this one is a much more straightforward approach, right? Okay, so let's proceed to another question. 5.7 says now calculate the mass of the SO3 produced, right? So remember, we have already concluded that this is the limiting reagent. And then when it comes to calculating any other substance, we know that we will have to compare it with the limiting reagent. So if we want the mass of the SO2 produced, we first need to say what is the ratio of the SO2, which is the limiting reagent, to the ratio of that SO3, which we are looking for, right? The product. Now the ratio we can see from here, the coefficients, that it is 2 is to 2. Remember, 2 is to 2 can be simplified further to 1 is to 1. And then remember, whenever we have a ratio of 1 is to 1, this simply means that the number of moles is the same, right? So the number of moles of the SO2 is the same as the number of moles of the SO3. You will remember that in 5.5, we've already calculated the number of moles of this. So that means, in other words, therefore, the number of moles of SO3 also has to be 1.56 mole, because we also calculated the number of moles of that. It was 1.56 mole. So if the ratio is 1:1, that means they have the same number of moles. Therefore, the number of moles is also 1.56 mole. But then remember, let's not get carried away. We are looking for the mass. Now, how do we calculate the mass? We know the formula is mass is equals to N multiplied by the molar mass, right? And then the number of moles 1.56. Then the molar mass, obviously, we have to consult with our periodic table. Sulfur is 32 grams per mole, and then oxygen is 16, but then we have 3 atoms of oxygen, so that's 3 multiplied by 16. Now, when you do that one, it's supposed to give you 80 grams per mole. Then what do? You simply just take the 80 multiply here, and then your mass will become a 124.8 grams, right? So it's grams, right? The SI unit for mass is grams, not grams per mole. So looking at your memo there, they wrote grams per mole, which was a mistake, right? So be careful when you are using the app to practice, note that mistake. Instead of saying grams, they said grams per mole. So you need to be careful of that. The SI unit for mass is grams. The SI unit for number of moles is mole. And then the SI unit for molar mass is grams per mole, right? So note that. Okay, so with all that being said, guys, please press the thumbs up button if you have enjoyed the lesson and then you have found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.